then feel free. So in this lesson today, we're going to talk and look about the definitions and calculations for moment of inertia, angular velocity, and angular momentum. And we need to know definitions, we need to know the calculations, and we need to know the units of measurement. And as we do that, we're actually going to tick this area off as well. So we're going to have a look at the factors that affect the size of moment of inertia, the mass of a body, and the distribution of mass from the axis of rotation. Yeah, so we're going to look at these three quantities of angular motion, how we are measuring angular motion. So I would split your page after you've given yourself a title, Quantities of Angular Motion. Split your page into two. So for Jacob, that's page of A4, title. I just split my page like this. And talk about linear motion over here and angular motion over here. So linear motion, we looked at inertia last year, and you should already know inertia is the resistance of a body to change its state of motion. So in angular motion, rather than inertia, we have moment of inertia, and that's just the angular form of inertia. So the definition is really simple once you know the definition for inertia, because all we do is stick angular in. So the resistance of a body to change its state of angular motion. That's the only difference. And the concept is exactly the same as inertia from last year. So a resting body does not want to start rotating around its axis. Remember when we talked about inertia, we talked about a body not wanting to change its current state of motion. If something has a large inertia, then it's difficult to move, or it's difficult to accelerate, or it's difficult to slow down. So in terms of moment of inertia and angular motion, an object or a body with a large moment of inertia is difficult to start to rotate, or it's difficult to stop rotating or speed up rotation. The amount that the body doesn't want to change its angular motion is the moment of inertia, and there are two factors determining the size of moment of inertia. And the first one you would be able to guess, okay, because it's linked to inertia from last year. So we know that moment of angular motion is created through the application of an eccentric force. So if we were to apply an eccentric force, push this ice skater on the side of his body here, and similarly an eccentric force to push this ice skater on the side of his body there, which would be the easiest to start to rotate, to change their current state of angular motion? I think we would all guess that this one would be the easiest. So this person has the largest moment of inertia, and that's because of their mass. This person has a smaller moment of inertia, again, because they have a small mass. So it's easier to make this person start to rotate than it is to make this person start to rotate. We require a smaller force, or a smaller eccentric force. But moment of inertia isn't just determined by mass. So inertia, we'll think about the calculation later. I don't want to confuse you, sorry. So moment of inertia then, not only determined by mass, but also the distribution of mass from the axis of rotation. So which, again, would we say here is going to take the smallest amount of force to make it rotate around its axis of rotation? If we say the axis of rotation for this tucked diver is here, so the axis is sort of through there, that would be the transverse axis, wouldn't it? And then the axis of rotation here for this one. So I'm going to apply an eccentric force here to make him rotate. I'm going to apply an eccentric force here to make her rotate. Which would require the smallest force, assuming they're the same mass, do you think? And I know you would have said this one requires the smallest force because it's a tuck position. We know that in a rotation, you would already know that it's easier to rotate when you're in a tuck position than when it is when you're in a straight position, okay? And the reason for that is the distribution of mass from the axis of rotation. So what we mean by that is, this is the axis of rotation. By tucking in, the diver, Tom Daly here, is tucked his head in so that this distance is as small as it can possibly be. He's even curled his toes up, look, so that this distance is as small as it can possibly be. In this tuck position, this distance is as small, this distance is as small, he's distributed his mass as close to this axis of rotation as he possibly can in order to reduce his moment of inertia as much as he can. This trampolinist, instead, has distributed her mass away from her axis of rotation. She's in fact pointing her toes to get her axis of her mass distributed as far from the axis of rotation as she possibly can. And this distance, it's called the perpendicular distance. So the perpendicular distance from the axis of rotation here is much greater than the perpendicular distance from the axis of rotation here. And this is reducing the moment of inertia and effectively making it easier to rotate. So Tom Daly's doing this here so that maybe you can fit in 3.5 rotations or forward somersaults rather than 2. And I would say that the trampolinist is in a straight position because she's showing off. She's showing that she can do a harder rotation in this straight position, or she might be about to land, so she's straightened out in order to slow down, to slow her rate of rotation, and we'll look at that next lesson. So there are a few applications of this in sport. So again, we could say that both of the legs are the exact same mass here in the sprinter. The drive leg, which is the back leg here, has a larger perpendicular distance from the hip. So the hip is the axis of rotation here, and this distance from here to here is much greater than the distance from the hip to here. Okay. So the perpendicular distance of the drive leg is much greater than the perpendicular distance from the axis of rotation for the recovery leg. And what that means is the recovery leg rotates around the axis much more quickly. And it does so with a smaller muscular effort, a smaller eccentric force. So sprinters would work to gain as much flexion at their knee as possible and as much dorsiflexion at the ankle as possible in order to reduce the perpendicular distance as much as possible in order to reduce the moment of inertia and therefore the required force. So I would say this is a poor technique because this sprinter needs to work to bring their toe closer to the shin, which would reduce the perpendicular distance and therefore reduce the moment of inertia. It's one of the things that sprinters do work on, driving from the blocks, really at getting as much dorsiflexion at the ankle joint as they possibly can in order to increase that rate of turnover as they drive out. Another application here, if we were to compare, let's say this is the same swimmer, so same mass, both arms have the same mass, and in the same pictures have the same mass. So the arm in the front crawl is flexed at the elbow, which gives it a smaller perpendicular distance from the shoulder. So the shoulder joint is the axis of rotation. That distance there is the perpendicular distance. The mass of the arm is distributed as close really to the axis of rotation as possible, giving this arm that's out of the water a really small moment of inertia and therefore quick rate of turnover. If we compare that to the butterfly, obviously we've got the axis of rotation in the shoulder. Now we've got a really great perpendicular distance as far as it almost as it can be, and this means that the moment of inertia in the butterfly for the arms is much, much greater than it is in front crawl, and therefore the stroke rate, the turnover rate, is going to be slower due to that larger moment of inertia for the butterfly swimmer. Okay, so not only we do it, so that's the sort of definition of moment of inertia and what it actually means and how it can impact sports performance, what we also need to be able to do is calculate moment of inertia. So we already know then that moment of inertia is determined by mass. We had the bigger ice skater compared to the much leaner ice skater, and we said that the leaner ice skater had a smaller moment of inertia. So it's determined by mass, and it's also determined by the distribution of mass from the axis of rotation. So we're saying that the moment of inertia here is smaller than the moment of inertia here because the distribution of the mass is closer to the axis of rotation. So we know they're the two factors that impact moment of inertia. So the calculation from there is pretty simple. So moment of inertia is the sum of the mass times by the distribution of mass from the axis of rotation. It can be written like this. So moment of inertia, mi, short for moment of inertia. This simple symbol means the sum of, and then we've got the mass times the distribution of mass from the axis of rotation, r squared. And therefore, when we put the quantities together, we get this unit, kilogram meters squared. So we've got kilogram is from the sum of the mass, and meters squared is from the axis, the distribution of mass from the axis of rotation, r squared. So let me give you an example. So calculate the moment of inertia during a biceps curl given a total mass of 10 kilograms and a perpendicular distance of 0.5 meters from the weight to the fulcrum. Remember, the fulcrum is the elbow and it's the acting as the axis of rotation in a biceps curl. Show your workings. Let me give you a clue. This is a past paper question, and there was something on this question that lots and lots of candidates overlooked. So have a think before you answer it. I wouldn't say there's a trick in this question, but there is something that lots of candidates overlooked. So maybe pause the video, give yourself a few minutes to do the calculation, then come back. So, as in all these calculation questions, write the equation first. It doesn't matter if you write out all the words or learn the short version. Obviously, this is going to take less time. Make sure, though, you do one of the two, because then if you get one of these figures wrong somewhere, you're still going to get a mark because you've shown that you know the equation. So moment of inertia is the sum of the mass times the distribution of the mass from the axis of rotation, r squared. So the mass is 10, but the thing that lots of candidates did in this exam is they just did 10 times 0.5, but it's r squared, okay? R squared, not just r. So we needed to do 0.5 times 0.5 to give us 0.25, and then 10 times 0.25. So your answer should have been 2.5, and then obviously kilogram meters squared, because this needs to have units in order to get the marks. So have a think, what's the effect of a longer arm? What would the effect on moment of inertia be of a longer arm? So let's say the arm were longer, but the same mass. So the mass is still 10 kilograms. It's a longer, leaner arm. So mass is still 10 kilograms, but now we've got a perpendicular distance of 0.7 meters. So we do 0.7 times 0.7 to give us 0.49, and then 10 times 0.49 to give us 4.9 kilogram meters squared. So a longer arm, a longer lever arm, gives us a larger moment of inertia, which means it's harder to make this body then move. So if this weightlifter had a longer arm with the weight out here, this now has a larger moment of inertia, and therefore it's harder to change its current state of angular motion. Now, a larger lever arm isn't always bad. Last year when we looked at levers, we talked about long lever arms generating large amounts of acceleration at the end. So for a discus thrower, A long lever arm allows them to generate a large amount of acceleration, so it works over a long range of movement and generates a large amount of acceleration, which ultimately means that they can let go of that discus at a really high rate of acceleration. So in some events, long lever arms are good, but for a weightlifter, long lever arms are bad because it increases the moment of inertia. And that's why usually weightlifters are short and stocky with short levers. It decreases the moment of inertia and means that they require less of an eccentric force, less force from the muscles to make that body change its current state of angular motion. So our second quantity, I would again on your page just do a little split it in half here, so you've got linear motion at one side and angular at the other. Because again, last year we looked at velocity. So velocity is the rate of change in displacement, and now this year we've for angular motion we've got angular velocity, and again all we need to do is drop this angular word in. So it's the rate of change in angular displacement, or in simple terms, the rate of rotation. How fast is something turning about its axis of rotation? So, therefore, if the same force or torque is applied, a torque is just another word for a turning force. So, last lesson you looked at that tennis ball and the application of an eccentric force which passes outside the centre of mass and generates angular motion. That another word for this eccentric force is a torque, a turning force, a force that results in something turning about its axis of rotation. So if the same force or torque is applied, a body with a smaller moment of inertia has a small resistance to rotation and therefore a greater angular velocity if we applied the same amount of force to it than a body with a large moment of inertia. So either or both of a large mass and or a large distribution of that mass from its axis of rotation. The same body will have a larger angular velocity when the mass of the body is distributed closer to the axis of rotation and the resistance to rotation is low. Angular velocity decreases when the mass is distributed away from the axis of rotation and the resistance to rotation is high. Now, that sounds complicated, but if you're sat currently on an swivel chair, you can demonstrate this to yourself now. So on your swivel chair, if you push your foot against the floor and send yourself off so that you start rotating about the axis, you're applying an eccentric force or a torque that generates some angular motion. Now you can, if you stick your arms out to the sides in a T shape and stick your legs out in front of you, you will feel yourself to slow down. Angular velocity will reduce really quickly. If you then tuck those arms into your chest and bring your knees towards your chest, you will feel your angular velocity increase. And as you distribute that mass again away from the axis of rotation, you'll feel your angular velocity decrease again. And then without touching the floor, without applying any extra torque, any extra turning force, if you pull those arms and legs back to your centre, you will feel your rate of angular velocity increase again. So that's obviously an application that you can do in your room. Let's think of, can you think of any sporting examples of that? So I would say the best sporting example is the one that we looked at earlier with the trampolinist and diver. So we've got a diver in the tuck shape, and their rate of angular velocity is much greater than the trampolinist in the straight shape. Their rate of angular velocity would be much slower, even if they had exactly the same mass and they applied exactly the same amount of torque on takeoff. The object, the body that's in the tuck position and with its weight distributed closer to the axis of rotation would rotate much more quickly. Its angular velocity would be much higher than the athlete in the straight position. Okay, so again, we need to look now at the calculations. So a quick bit of revision here. Velocity. Last year we looked at this. The velocity equals displacement over time, measured in meters per second, because displacement is measured in meters and time is measured in seconds. So this year, angular velocity, again, it's really easy. We just need to put the word angular in. So this time, angular velocity is angular displacement over time. The biggest difference here is angular displacement is not measured in meters, and it's not measured in degrees either, as you might expect. It's measured in radians. So angular displacement measured in radians, time still measured in seconds, and so angular velocity is measured in radians per second. So this is a picture just to show you what a radian is. Obviously, you know, a semicircle, you would already know that that is 180 degrees. Well, 180 degrees, a semicircle, is 3.1 radians, it's pi. Now, you don't need to know this, I just wanted to show you this so that you understand why angular displacement is measured in radians. It's a radian is a way of measuring this sort of rotation, this degrees of separation, this degree of movement around an axis of rotation. Okay, like I say, you don't need to know this number, you don't need to know what this means. I just wanted to show you what a radian was. So we've got a trampolinist here, axis of rotation, again the hip. They're moving from this position here into this position here, so they've moved through 90 degrees, which would be just over 1.5 radians, 1.57 radians to be exact. So can you use the calculation in order to calculate the answer to this question? A trampolinist performing a seat drop rotates their legs clockwise about the transverse axis, because it's this one coming through here, isn't it? 157 radians in 0.5 seconds. Calculate the average angular velocity. Pause the video, have a go. Okay, so hopefully this was a really easy question. We've got angular velocity is angular displacement over time. Angular displacement measured in radians, so it was 1.57 radians divided by time in seconds, 0.5 seconds, gives 3.1 radians per second, and obviously you needed the units as well as the number in order to get the marks here. Okay, finally, momentum versus angular momentum. So again, if you split your page in two so that you've got linear motion over here and angular motion over here. Last year we looked at momentum, defined momentum as the quantity of motion possessed by a moving body, and again all we need to do this year is drop in this word. So angular momentum is the quantity of angular motion possessed by a moving body. Easy. So in order for a sporting body to rotate, angular momentum must be generated. How do we generate angular momentum? You should have looked at this last lesson. Where you would have looked at an idea similar to this, forward somersault. So this gymnast is throwing a weight forward at takeoff, which moves the centre of mass outside the body. It means that when she applies the action force into the floor, the reaction force that's generated travels outside of the centre of mass, therefore creating an eccentric force or a torque force, which generates some angular momentum and allows her to have angular motion in the air. So if you're not clear on this yet, it might be worth noting this down. You might be absolutely happy with this. So in the preparation phase, an eccentric force or torque must be applied in order to generate some angular momentum. So here the gymnast leans forward, so the reaction force generated from the floor passes outside of her centre of mass. It creates an eccentric force and generates some angular momentum. And finally, the calculation for angular momentum. So last year we looked at momentum, mass times velocity, obviously measured in kilogram meters per second, because mass is measured in kilograms and velocity is measured in meters per second. Now this one is slightly more complicated because angular momentum is not just about mass, is it? We know that it's about mass, but it's also about the distribution of that mass from the axis of rotation. So rather than just having mass in the equation for angular momentum, we put moment of inertia in the equation, and that means we're factoring in not only mass, but we're also factoring in the distribution of mass from the axis of rotation. And we times that by angular velocity this time rather than velocity. It's got the most difficult unit here because we've got moment of inertia measured in kilogram meters squared, and we've got angular velocity measured in radians per second. So angular momentum is measured in kilogram meters squared, radians per second. It's the most complicated unit, but if you write out the equation and you know the unit for moment of inertia is kilogram meters squared, and you know the unit for angular velocity is radians per second, all you need to do is sandwich those together to give yourself the units. So have a go at this calculation then. A 60 kilogram gymnast performs a tucked front somersault. In the tucked phase, their moment of inertia is 15 kilogram meters squared, and they rotate with an angular velocity of 8.0 radians per second. Calculate their angular momentum during the tucked phase of the somersault. Have a go and come back to the video. So hopefully you first of all wrote out the equation, angular momentum equals moment of inertia times angular velocity. You knew the moment of inertia was 15 and the angular velocity was 8. Timesing those together gives us 120, not to forget the units kilogram meter squared radians per second. And that's that for this lesson. So we've looked obviously at definitions of moment of inertia, definition of angular velocity and definition of angular momentum, and I've given you some sporting examples of where they are in each can be seen and where they're really important in certain sports. We've also revised the definitions of inertia, velocity and momentum, those quantities of linear motion that we looked at last year. Plus revising the calculations and units of those things and adding on the calculations and units for angular motion for a moment of inertia, angular velocity and angular momentum. Okay, and then finally we looked at the fact that moment of inertia is affected by not only the mass of a body, because inertia is affected by the mass of a body, but that moment of inertia is affected by the mass of the body and the distribution of that mass from the axis of rotation. So next lesson we're going to start to look at the relationship between inertia, moment of inertia and angular velocity, and some other bits and pieces to do with angular motion.